Welcome back to this week of digital forensics and penetration testing. This week we're going to be talking about network forensics and network traffic and analyzing that. And in order to do this, we need to have a basic understanding of how networks work. Now, I know some of you have already taken a networks course or have more extensive network knowledge, but this will be a review for those of you who have already studied some networks, and those who have not. This will give you a solid foundation to help you learn more on network fundamentals and network foundations. So, why do network fundamentals matter? So, network attacks, data exfiltration events, intrusions, they all leave traces somewhere. A lot of times you can look at an individual system to identify the indicators of compromise or how a malicious actor got in. But frequently what you will have is you will have a network packet capture, or you will have a seam or IDS or IPS somewhere at the network level, which is tracking all of this. And you'll have to look through those logs and understand the life cycle of a connection to really identify what happened, how it happened, and what the indicators are. So without understanding those protocols at a technical level, you can't really distinguish what is malicious and what is benign traffic, and be able to identify those covert channels or reconstruct different attacker intentions or actions, or even be able to analyze like data exfiltration. So it's very important for threat detection, incident response, like I had mentioned, penetration testing. So understanding and knowing how network and the network stack functions will allow you to test it and try to compromise systems using the network stack through malformed packets or through things like a SYN scan or a port scan, something of that nature. So a lot of you are familiar with the OSI network model. That is 7 layers. The layers are physical for layer 1, layer 2 is data link, layer 3 is network, layer 4 is transport, layer 5 is session, layer 6 is presentation, and layer 7 is application. And the OSI network model was one of the first and still most widely used theoretical network modeling ideas out there. There's also this TCPIP model, which is a little bit more practical, but it does encapsulate some of what the OSI model has just into a fewer number of layers. So on this model, and we're going to start at the bottom, the layer 1 is listed as network access. This is really a combination of layer 1 and layer 2 of the OSI model. So layer 1 being the physical layer, which is the actual cables or the radio signals going across the air, the fiber optic cables, anything of that nature. And then layer 2, which is data link. And so when we talk about networking, the device which lives at layer 2 is the network switch, and the data type which lives at network 2 is the MAC address. MAC address being a physical hardware address, which is assigned to every single device. So every device in the world will have a unique MAC address assigned to it. And if you have a data capture or network capture from an internal network, that MAC address for those internal devices would point you to a specific device there. Now, there are various attacks and ways to kind of spoof that through MAC address spoofing and other sort of attacks, but you can still use that MAC address to say, this is the device which is actually at that particular location. So it is a physical hardware address and it is assigned by the vendor, although it can be changed. Going one layer up in the TCP/IP model is the internet layer, and the OSI model is known as a network layer. And this is where the device known as a router exists, and also the data type of IP addresses. those are all at the internet layer. And this is the same in the TCP/IP model. So the difference between a switch and a router is a switch is a lot like train switching system, to where you have a series of tracks and you're just switching the trains or the data from one track to another track. There's really no sort of logic there or anything. It's just a hardware device which allows traffic from one port to go to another port on the same switch, or gets switched up to a different switch that may end up passing it out there. And that all uses that MAC address. Working at this internet layer, or the network layer in the OSI model, now you have routers. And routers are what allows networks to talk to other networks. And so in order to facilitate that, you need an IP address. And we'll talk a little bit more about IP addresses in the next group of slides, or the next PowerPoint. But the IP address is effectively a phone number for a device. It can change. It is not necessarily always tied to a particular device, but it allows someone to dial up that individual or dial up that specific device and be able to send traffic back and forth. So at the internet layer, you'll have IP addresses. You'll also have ICMP, which is Internet Control Messaging Protocol. This is also commonly known as pings. So a lot of you have run the ping command, and all that does is send a small amount of data to a remote location and then time how long it takes to go there and come back. And so like if you're playing a video game, the ping times are typically your communication between your computer and the game server wherever it is hosted. If you ping a website, then that is going to be from your computer to that web server and how long it actually takes to get there and back. So at this particular layer, you need to know the source and destination IP address. There's a TTL value, which is known as a time to live. And that is a value designed to prevent routing loops. So what could happen is, as traffic is traversing the internet or a bigger network, there may be a loop to where it bounces between several routers and just gets caught in a loop there. Every time that it traverses a router, it subtracts from that TTL, and if that TTL ever hits 0, then the routers assume that there is a routing loop and just tosses that particular packet. And so a way to kind of leverage that, and I've done this before in the networks class, is you can create a traceroute program. And a traceroute program, all it does is map out from your computer to another computer, which routers does it talk in that particular path. And so at each step, you just add one to the TTL, and that will go increasingly through the router list. And each time that the router tosses it, you record that last hop, and then you send a new packet with a slightly higher TTL. And that will allow you to map out the network and map out the path. Fragmentation, this is another key thing in network technology. Data gets fragmented. And by fragmentation, what I mean is, if you have a really large data stream or a really large data packet, it will take that large packet and break it up into smaller segments and send those across the data stream. And then at the receiving side, it will take all of those fragments and recombine that. Some of the uses of IP addresses, geolocation. So we talk about this in the networks class, and so I'm not going to go over it too much here, but at IP addresses, especially public IP addresses, are assigned by regional internet registrars or registries known as RIRs. There are 5 of them spread across the world. There's ARIN for the North America, which is Canada and US. And there is LACNIC, which is the Latin America, which is Mexico all the way down through South America. There is RIPE NCC, which is Europe. And there's also AFRINIC, which is Africa. And then there is APNIC, which is the Asia Pacific and Australia. So IP address blocks are assigned to those RIRs, and they're responsible for handing out blocks of addresses to customers inside of there. So if you have an IP address, you can take that address and get a idea as to where that address is assigned and what physical country, or a lot of times you can even get down to the exact city that that IP address has been assigned to. Moving one layer higher is the transport layer, and this is named the same in the OSI model. This is where many of the protocols tend to live. And two of the most important protocols, and we will talk quite a bit about TCP, is TCP and UDP. TCP standing for Transmission Control Protocol, and UDP stands for User Datagram Protocol. These are two very important protocols, but they perform completely different. TCP being a two-way handshake-oriented connection protocol, whereas UDP is just really kind of like pointing a fire hose at something and sending data and hoping that the receiving side can deal with it. So video streaming, voice over IP, a lot of video games, those all use UDP for its traffic, whereas TCP, the internet by and large uses TCP. Financial transactions, that all uses TCP. Anything that you need to make sure that the data gets there in the correct order and is complete, you would use TCP for that. To accomplish this, you need to have what's known as port numbers. And port numbers, and we will talk about this a little bit more also, these are a number that you can kind of think of your network connection. You have a wall sitting in between your network connection and the internet. If someone wants to come into your network, then they have to go through a specific port. And a port is effectively a hole or a doorway in that particular wall. And so there are different port numbers for different purposes. And I have another slide, a couple of slides later, which will talk about some of the common ones. But things like port 22 is used for SSH. Port 80 is used for HTTP. Port 443 is used for HTTPS. So anytime that you have a service that needs to have incoming connections, there needs to be a corresponding port number assigned to that and opened in that particular firewall. With TCP, like I had mentioned, there's also connection states. These are the flags as part of TCP. Some of the flags are a SYN flag, an ACK flag, a FIN flag. There's also a push, a reset. There's a couple of other flags out there, but a lot of what you will see will be SYN, ACK, and push flags for a lot of the stuff. There's also sequence numbers, there's acknowledgement numbers, there's window size, there's checksums, there's quite a bit of stuff out there for that. Going one level higher, there's the application layer. So now in the OSI model, this is three separate layers. And in the TCPIP model, they just took all three of those layers and combined it into one application layer. And this is really where applications live and software lives, and sockets tend to get created, and servers and services end up working. So there's more server-related stuff there, service-related stuff in the application layer. And as you go down through the model, that's going to be more the network-related technologies. Now, data, as it traverses a network, it starts at one of the layers, one of the upper layers, say the application layer, and as it goes down the model, it adds information to the header. So it's known as data encapsulation. So if you are making a connection to a web server, it will start at the application layer. It will take that request, send it to the transport layer. The transport layer will add on the TCP information, so the port that it wants to talk to, the port that it's coming from, connection state, et cetera, et cetera. Then it will take that data packet, send it down to the internet layer, where it will add on to the beginning of this the IP address information and everything else which corresponds to the internet layer. Then it will take that entire packet, pass it down to the network access layer, where it will add on the Ethernet or the MAC address information, and then it will pass it on to the physical layer, send it across the wire, and as it traverses the internet, it will move up and down this model until it gets to the actual destination. At each time that goes to a location, it will start moving up that model, stripping off the header and checking to see, okay, do I pass it on to something that I control, or do I pass it on to the next router in the line? And so packets will go up and down this model quite a lot as they traverse the internet. And then when it comes back, it just does the exact same thing. So TCP connection lifecycle, and this is a standard TCP or transmission control protocol connection. It begins with what's known as a SYN, or a synchronization packet. So a client will send a SYN packet with a sequence number, and it will be a randomly generated sequence number, and it will also have some port. It will have both a destination port of what it wants to talk to. So if it wants to talk to a HTTPS server, it will have a destination port of 443, and its source port will be some randomly chosen number above 1024. And this is operating system dependent, but it will be some random number. So on Windows, for instance, it may be a number like 49,123. And every time it makes a new connection to someplace, it will choose a different random high numbered port. Once that packet gets to the server will then respond back with what's known as a SYN-ACK packet. And so it will take that sequence number that was in the SYN packet, move it down to the acknowledgement field with, it will take that number and add one to it, move it into the acknowledge, and it will generate its own sequence number, and then it will send that data back to the client. Then the client will take that same packet and it will again swap the sequence and acknowledgement numbers, adding one as needed, and it will send back an acknowledgement. So it's this three-step process at the beginning of every connection that basically says, hey, I want to talk to you. Server says, okay, I want to talk to you too. And then the client says, thank you, let's go ahead and talk. Once that happens, then data can flow back and forth between the client and the server over the existing established connection. Once this connection is done, then either the client or the server, whoever initiates the close of the connection, will send a FIN, and then there will be a FIN-ACK from the other side, and then that side will also send a FIN and then a FIN-ACK from the corresponding other side. So for instance, if the client is done talking with the server, the client will send a FIN packet, server will respond back with a FIN-ACK, then the server will send a FIN packet, and the client will respond back with a FIN-ACK. At that point, then the connection is closed and all the resources are released. There's also an RST or reset packet, and this is something which can happen sometimes with a little bit of regularity, but that just means that there's a reset in the data connection, TCP connection. So from a forensic standpoint, when you're looking at packet captures and traffic of that nature, if you see a client send a lot of SYN packets to some server, but you don't see a corresponding SYN-ACK, then that may be a closed port. If there's a SYN packet which is sent back with a reset, then it may be filtered by the firewall. If you see a lot of SYN packets spread across many ports from a client, well, then that may be someone using or running a port scan on a particular host, trying to find which ports are actually open. And there's a lot of programs out there which will look at if there's a number of SYN packets above a set threshold, then it just blocks that particular connection, because it means that someone is constantly jiggling all the doorknobs and trying all the windows to see what is actually open, not necessarily breaking in, but it's more reconnaissance to see what is listening at that particular location. So moving to DNS. DNS stands for Domain Name System. This is, well, it's the internet's phone book, basically. This is a records list to basically convert from names to numbers. So a lot of you are familiar with DNS names. So youtube.com or google.com or something of that nature. Those are different DNS names. And so names don't really map to anything, but the address, the IP address, is where the actual server or service ends up lying. So there needs to be a mapping from a name to a number. So anytime that you go to www.google.com, you're actually going to a specific IP address, but you don't need to know that IP address. So in order for that to happen, there needs to be a DNS record, and more specifically an A record or a quad A record. And that will map a specific name over to a specific IP address. So the difference between an A record and a quad A record is A is for IPv4, quad A is for IPv6. There are a bunch of other records which we aren't going to deal a ton with, but it's still useful to know. There's MX records or mail exchange records. This is when you send an email address, say user at somedomain.com, that somedomain.com would have to have an MX record to tell the mail server where it needs to talk to deliver that particular message. So you can see in this slide here, there's the example.com MX record points to mail.example.com. And so that would be user at example.com, for example. There's also what's known as a text record. And this is used a lot for things like SPF, which is Sender Policy Framework, for email validation. It's also used for domain validation. So if you look at a particular DNS record or a domain name and you look at their text records, there may be a lot of different validation strings in there for different services like DocuSign or Apple mobile services or something of that nature. So a lot of times if it's a malicious domain, they will have some really weird or arbitrary text records that may not correspond to any known service or anything, and that's how it's using it to behave as a command and control domain or to point systems to some other address there. There's also pointer records, and this is if a normal A record maps names to numbers, pointer records map numbers to names. So this is not as common on the public internet. It does happen sometimes, but it's more common inside of corporate or enterprise type networks to, if you have an IP address, it will map to a corresponding DNS name. So it's just a reverse record. And then the last one is CNAMEs, and these are aliases. So this is how you can go from, say, mail.example.com to get directed to some other domain .example.com. Or in this particular example that it has here, you can go from www to corp.example.com. So it's just a way of aliasing from one domain name or one subdomain to another subdomain or another domain. And then that other domain would then maybe have an A record for it. So you can kind of trace this. If you go to www.example.com, that will redirect to corp.example.com, which then that will redirect to 203.0.113.10. So it's just kind of following that particular path. Looking at HTTP and HTTPS, these are different web technologies. So Hypertext Transport Protocol and Hypertext Transport Protocol Secure. This is web pages. The main difference between these two is HTTP is over port 80 and HTTPS is over port 443. Port 80 is unsecured. So anything which is sent to HTTP is in the clear across the entire internet. So routers, potentially other users on the network, other servers and systems can actually see all of the data which is being sent across an HTTP connection. There's all sorts of different things that can go into it, and we don't have enough time for all of this to talk about it, but you can get user agent information, which will reveal kind of the browser type or the operating system type. There's cookies, which are part of information which is stored whenever you visit a website, or maybe session tokens, things of that nature. There's response status code. So if something works correctly, then it's a status code of 200. If it's not found, it's a 404. If it's not authorized, it's a 403, so on and so forth. HTTPS is secured with SSL. And you can read through all of this. And again, there's a lot of discussions that we can go into on how this all works and everything. But basically, it's an encrypted connection that anybody watching that connection would not be able to see what's going on. Now, in order for that to happen, the beginning of the connection needs to have what's known as a TLS handshake. And this is the client hello part. And when that happens, then it actually will have to transfer some information to the server, and the server will have to transfer some additional information back, and then it will start that encrypted connection between there. So from a forensic standpoint, there's a decent amount of information that you can actually glean from this. So you can look at traffic volume or timing patterns. You can look at fingerprinting of that to identify like what type of client application or what type of service it's actually using. There's the SNI field, which is the server name, which is additional information that could get leaked out. So even with HTTPS, which is making the entire internet more secure, there's still a decent amount of information which is exposed that may be forensically valid. Talking about the ports, because we were talking about that with TCP. These are some common ports that would be worth kind of memorizing. So FTP, which stands for File Transfer Protocol. It's an older transfer protocol, but it is very, very fast. Uses ports 20 and 21 over protocol TCP. So you'll notice that most of these are all just TCP. And it's just because it's a two-way connection-oriented protocol. Port 22, again, SSH, which is secure shell, so that you can remotely log in, or somebody can remotely log into a system through a terminal connection. It's used a lot by systems administrators, network administrators, but it's also used by malicious individuals quite a bit. Port 23 is Telnet. Nobody should ever use Telnet. Sometimes it's still in use on the internet, but it really shouldn't. It's just unencrypted, shouldn't actually be used. Port 25 is SMTP. That's for sending emails. Jumping down a little bit, you'll see port 110 and 143, which is POP3 and IMAP. That's for receiving emails. Again, SMTP and POP3, IMAP on those ports is unencrypted. There is an encrypted port version, which is higher up, but you may still see some SMTP servers or POP3 or IMAP servers out there, so it's useful to know those particular numbers. Port 53, that one is both TCP and UDP, and this is for DNS records and name resolution. So if you had to do a DNS lookup, it would send it over port 53, and it would get back a response over 53, or it's either 52 or 53. I can't remember which one it actually gets a response back over. But that one is for DNS. Port 80, like I had mentioned, is HTTP, and 443 is HTTPS. So those are the web traffic. There's a couple of other higher number ports, and you can see it at the bottom there, which is 8080 and 8443. Those are unofficially for HTTP and HTTPS, but they've been in common usage for those. Port 445 is SMB, or server message block. This is for file sharing on Windows computers. And this is something which A, should never be on the public internet, B, should be heavily secured even on a corporate network. There was a couple of vulnerabilities back in the day, Eternal Blue and WannaCry, which leverage the SMB file shares that were on every single Windows computer and were exposed inside of a network, and those were able to spread and control Windows computers pretty easily. One of the other really super important ports that you should never, ever, ever see on the public internet is port 3389, or Windows Remote Desktop Protocol. I've shown this in some of my classes, and you can easily look this up. If you log into Shodan, you can do a search for the internet for any IP address that it has tracked running port 3 or having port 3389 exposed. And last time I looked, I think there was like 1.5 million addresses which had port 3389 exposed. This allows you to remotely control Windows computers. There are a lot of beneficial uses for it, but it is also really, really dangerous when it's available on the internet, because, well, there's not a lot of security with it. There's not a lot of monitoring, and it is a pretty significant vector into a network. Port 4444 is Metasploit, and we'll use Metasploit a little bit more later on, but this is the default Metasploit reverse shell. There are other ports, but generally, if you are running your own system or you're looking for malicious systems or services, you're looking for something which is from port 1024 or higher, up to 65,530, 65,000 some odd number. That's because anything from port 0 to 1023 is a well-known port, and it is administered by IANA, and it requires administrator or root permissions on a system to actually bind to one of those lower ports. So just keep that in mind, that you'll want to roughly know these ports just in general, but in a lot of analysis, if you're looking for indicators of compromise, usually you're looking at ports which are above 1024, because that's things that anybody on a computer can open typically. Speaking of indicators of compromise, DNS tunneling, so unusually long subdomain labels. So sometimes you will see a domain and the subdomain, so a domain is google.com and a subdomain is www.google.com. Anything to the left of the domain is known as a subdomain. So if you see a really long subdomain to the left of the actual domain, say greater than 50 characters, that is a little strange. I mean, there are legitimate uses for that, but it's also something which could give pause and warrant additional investigation. A lot of high frequency queries, or a lot of queries, really large text record responses or frequent text record responses, queries of random looking subdomains of one domain. There's a lot of ways to kind of leverage DNS, just because DNS is required everywhere, that attackers can embed information in some of the DNS records that may slip past various other protections that may be in place. There's also HTTP beaconing, so periodic outbound requests at a regular interval, or consistent timing, small fixed size payloads, request to IPs rather than domain names. Those are all indicators of command and control infrastructure. So if you have a compromised system which is talking to a command and control system, well, there may be some HTTP beaconing that would be discoverable. There's also credential tunneling, so SSH or HTTPS on non-standard ports. There are legitimate reasons to not run SSH over port 22, largely to avoid people from port scanning someplace. But that could also be an indicator that something malicious is going on. Or ICMP payload, so like I mentioned, that's the ping. It's really, really small, typically 32 bytes in size, but the actual ICMP specification, you can make it quite a bit larger. So if those payloads get large, well, then that might be an indicator that something malicious is happening, or encrypted sessions, connecting to unusual IPs or geographic locations. All of this on its own may not be a problem, but if you start looking into it, those are clues that could point you towards some indicator of compromise or some issues out there. Port scanning, I had already mentioned this, but this is rapid SYN packets, and there are several different ways of doing port scanning, but one of the common ways is lots of SYN packets sent to several different port numbers or sequential port numbers, spread across one host or maybe even multiple hosts. So Nmap, which is a very common network utility, will do a port scan, typically using a SYN scan by default. It is tunable, but that is usually the default. So I already talked about this, but every network packet has headers on it. So looking at it, if we kind of start at the bottom of this, if you have your particular payload, so in this case, this is the HTTP payload, as it traverses, it moves up and adds in the TCP header. TCP header is 20 bytes at minimum, could be as large as 60 bytes because there's options that can be added in there, but you'll have things like your source port, your destination port, sequence number, acknowledgement numbers, any sort of flags. There's a data offset, reserves, window size, checksum, and an urgent pointer, which really isn't used. And that is something that if a network administrator is looking and sees an urgent pointer being set, well, that's strange in this day and age. Once it moves up to the next header, it adds in the IP header. And so typically with the IPv4 header, that's going to be 20 bytes, and it will have version, the actual address, the source and destination address, checksum, et cetera, et cetera. And then moving one layer up is the Ethernet header, which will add in the MAC addresses and the Ethernet type, and that's typically 14 bytes. So at a minimum, every data packet adds in 54 bytes of additional information when it gets sent out. Now, 54 bytes isn't a ton, but it just kind of depends upon what you're actually doing and whether or not that may be an issue. UDP, if it was using UDP instead of TCP, that header is quite a bit smaller. In fact, the UDP header is only 8 bytes in size versus 20 to 60. So when you look at Wireshark, you'll see all of this in there, and this will give you more of a sense of how an individual connection looks and kind of what its life cycle looks at. Wireshark is one of the best tools out there that you can ever use, and it's one of those which you just need to use it and get comfortable with it, and it just takes a little bit of time. So takeaways, like I said, TCP/IP model has 4 layers versus the OSI model has 7. They're both comparable. It's just 2 different ways of representing kind of the network lifecycle. TCP has that 3-way handshake of SYN, SYNAC, and ACK. It's a fundamental forensic landmark. Any changes in that could be indication of something going on. There's also DNS records, which I talked about. HTTPS, which is the encrypted version of HTTP, but there's still some information which is leaked out. There's protocol anomalies and things of that nature that generally you want to look at if you start seeing those on a network. And then you just need to understand the packet structure and the headers which are added on at each layer. And so as you use Wireshark more and more, then you will start to understand how all of this works together.